Hello, welcome to lecture 3. In this lecture, we're going to do more examples about waves. We're also going to find the velocity and acceleration of a traveling wave and discuss how James Clerk Maxwell managed to figure out that light was a wave.
In this example, we have a sinusoidal wave with an amplitude of 1.5 centimeters. Why don't we start making a list as we read? So we have a wave. That means it looks something like this. Let's think of it as a wave on a string. It has an amplitude of 1.50 centimeters. You can convert to meters or leave in centimeters. A frequency of 150 hertz. What should pop in your head now is that you could calculate at this point the period or the angular frequency. Travels at 300 meters per second. V equals 300 meters per second. And it's traveling in the negative x direction, so to the left. Let's put an arrow on our wave. At t equals 0, the point at x equals 0.5 meters is on a trough. That means it's at a low point of the wave. So y at a position of 0.5 meters and a time of 0 seconds, it's equal to a trough. That means it's at the negative amplitude, or minus 1.50 centimeters. Okay, that's a lot of information. Part A, determine or write down the values of amplitude, speed, wavelength, wave number, frequency, angular frequency, period, and phase constant. That's a whole bunch of stuff. The point of this example is just to see where do all these numbers come from. And even though it looks like you're not given enough information, you can actually figure out all this stuff. The amplitude is straight up given, 1.50 centimeters. The speed, straight up given, 300 meters per second. The wavelength, okay, the wavelength is not given, but you do have the speed and the frequency. We know wave speed is frequency times wavelength. So wavelength is speed over frequency, 300 meters per second, divided by 150 hertz equals 2 meters. Okay, we'll go on to the next slide for the rest. Next, we want to find the wave number. For this, we have to remember that our wave number k is 2 pi over the wavelength, lambda. So 2 pi over 2 meters gives us pi radians per meter. You can leave it like that, or you could write it as 3.14 radians per meter. Either of those two expressions is fine. Okay, next is the frequency. That's just given, 150 hertz. Omega is the angular frequency. That's 2 pi times f. So you can write that as 300 times pi, or you can go ahead and put in the numbers, which would give us 942 radians per second. What's left? The period t. We know period t is the amount of time for one oscillation. That's 1 over the frequency. 1 over 150 hertz. If it oscillates 150 times a second, we know that the period is going to be small. And it's 6.67 times 10 to the minus 3 seconds. Now, the phase constant phi, that one's a little bit harder. We're going to have to use some of the given information, and things we know is that at t equals 0, the point at x equals 0.5 meters is on a trough. We're going to have to use this information together with the equation of motion, or the form for the equation, to figure out the phase constant. In finding the phase constant, we have to think about where that fits into the equation. We know that in general, y as a function of position and time is the amplitude times the cosine of the wave number times x. Now, here, if it was a rightward traveling wave, we'd write minus omega t. We have a leftward traveling wave, which makes it plus omega t plus phi. Okay, let's just get a little note in there. Plus because traveling left. We know k, we know omega, we know a, we don't know phi. So what do we know? We know that if x is equal to, just going to switch colors right here. If x is equal to 0.50 meters, that's this bit, and if t is equal to 0 seconds, that's this bit, then the height of the wave is on a trough. It's at the negative amplitude. So this bit right here equals minus a, or minus 1.5 centimeters. We know K, we know omega, we can plug everything in and we can solve for phi. Okay, let's try that. So our y is minus 1.50 centimeters equals the amplitude, which is positive 1.5 centimeters, times cosine of K, 3.14. I'm going to sacrifice units for space, so 3.14 radians per meter, times x, which is 0.50 meters, plus omega, I'm just going to write that as omega, times t, which is 0, plus the phase constant phi, which we don't know. So this omega times t, 942 times 0, that's just 0. I'm going to divide both sides by 1.5 centimeters to get minus 1 equals cosine 3.14 times 0.5, that's 1.57, plus my phase constant phi. Okay, so that's a lot of algebra that I said out loud. I divided both sides by 1.5 centimeters. I multiplied 3.14 and 0.5 to get 1.57. I multiplied omega by 0 to get 0. So that's where everything in that equation came from. If I want to find my phase constant phi, I have to get rid of my cosine. So I take the inverse cosines of both sides. The inverse cosine of 1 is equal to. Now the inverse cosine of a cosine leaves me with the argument. This is something I can solve. The inverse cosine of 1 is pi. So that's equal to 1.57 plus phi. So phi is equal to pi minus 1.57. Pi is 3.14. We subtract 1.57, we get 1.57 or pi over 2. Okay, so there's our phase constant. That's in radians, and that finishes part A. Leads us right into part B. Write the equation of motion for the wave as it travels. That means write the height of the wave as it moves down the string. So y of x and t, the first thing you should do is write your equation in terms of symbols. If this were a test, you'd probably mention that you used a plus here because the wave is traveling leftwards. And then after that, you plug in your numbers. So y of x and t, that means the height of the wave depends on x and time, is equal to the amplitude, 1.50 centimeters, times the cosine of the wave number. We calculated that to be 3.14 radians per meter, times x, plus omega, which is our angular frequency, 942 radians per second, times our time t, and we add in our phase constant, 1.57. There's our equation of motion for the wave. Next part is to draw the wave at t equals 0. For the last part of the question now, we're asked to draw the wave at time t equals 0. So what I did here was I just wrote down the equation for the wave, so I just copied this from the previous slide. And what we're asked to do is draw it at t equals 0. So we put t equals 0 in here. That whole term goes to 0. So we're drawing a wave, which means we're drawing y as a function of x at t equals 0. So this is what we're doing for our picture. There are a few ways you can do this. You could open up an Excel spreadsheet, pop your equation in there and draw your graph. That's okay. You could make a table of data. So you could pick a whole bunch of values of x, calculate your y's, plot those points and connect the dots. That's basically doing an Excel spreadsheet by hand. Or you can think about what the information tells you and maybe use a little bit of intuition to draw it that way. I'm going to go with this last way. What I know is that if x equals 0.5, then y is the negative amplitude. So the first thing I'll do is I'm going to label my graph. So this is 0.5 meters, 1 meter, 1.5, 2, 2.5, 3, 3.5, 4, 4.5, and 5. Okay, so there are my x values. My y is going to have a maximum value of a and a minimum value of minus a. And a point that I know is that if x is 0.5, y is equal to negative the amplitude. So that's this point right here. Another thing that I know is that the pattern repeats every wavelength. So lambda equals 2 meters. That means y at 2.5 meters also equals minus the amplitude because it's at a trough again, one wavelength later. So I've got a negative amplitude there, and another wavelength later, another 2 meters down the line, again, it's at a negative amplitude. Okay, that's one bit of information. What's another bit of information? Well, in between two troughs, there has to be a crest. So every half wavelength, there's going to be a crest. So our crests are going to be right there. In between a crest and a trough, it has to go through an equilibrium. So I'm going to draw my equilibriums. Okay, now I've got a whole bunch of points, and now I'm just going to set out and connect the dots. It's not a perfect drawing, but it's not bad. You see that it's periodic. It's more or less sinusoidal. Excel would do a better job, but this is okay. This is acceptable. So this is y of x and 0 equals 1.5 centimeters times cosine of 3.14x plus 1.57. Okay, had to squeeze it in there. So that's what the wave looks like at t equals 0.